Okay, so let's continue looking at our class info created to help us look at different graphing types or visualizations that we can create from varying data types. So here I'm at my data sets. If you saved yours, you can work along with me, or this is a public file set for you all to access if you want to look this up under data sets. Okay, so a quick review before we move on. From last class, we came up with several graphs. Let me see if I can get those to come up for us. We came up with things like summary statistics. We talked about the importance whenever we're dealing with any type of variable, the importance of us looking to see if there's anything that just looks wrong, right? So we check out things like the range, the maximum, the minimum, right? Median and mean, we will discuss that a little bit later, how those two values relate to each other. But certainly we can at least glance at those now to say, hey, does something look way off? Does it look strange to me? And then, of course, sample size. Let's see, this is looking at the quantitative variables that we are about to explore more. Let's go back and take a look at some of the other graphs too, though, just to maybe help refresh everyone's memory. Let's see, it looks like we have a frequency table for siblings, pets, and music. So with these things, remember last class we said, hey, you know what, you can use a frequency table or even a relative frequency table, which is basically the same concept. Relative frequency simply divides each count by the total number to give you a percentage frequency. So, and actually in these we're showing both of these, frequency and relative frequency. So you can create this type of table for either type of data type, whether it is qualitative or quantitative. We notice that it looks very nice here with this qualitative data, and actually it's not as good down here with heights. It works in this case, but remember we said that was because of how this quantitative variable was put in. You see, even though we can use frequency tables with both data types, we do also want to consider discrete versus continuous. Discrete being separate values, like here, 61, 63, 664, where we're not allowing any decimals. There's no continuity from one input possibility to the next. And the reason that's easier for a frequency table is because whenever we're counting it kind of keeps us on a more finite list, a more reasonably sized list for what we're looking at when we're trying to understand the balance of what's going on with our data here. So even though technically height is typically a continuous variable, the way we put it in as a class, we entered this as whole numbers only. So we treated it as if it were discrete. In cases where decimal points were put in, where you'd actually had this huge range of actual values that you could have showing up in a frequency table like this. Typically, a statistician will use something called an interval, a class. StatCrunch calls it a bin, right? So these intervals or classes will say something, for example, like height between 60 to 61, height between 61 to 62, right? Where one of the 61s is inclusive, the other isn't. So we get these little intervals so that we can account for decimals in between without having so many separate elements in our frequency table. But again, this was another place that we said, you know what, before we start graphing, we do want to make sure that we don't see any red flags. So we check summary statistics, we check frequency tables, and we just take looks, looking for things like misspellings. Do I have words that where I've got pop with a capital P and then a lowercase p down below, where it's counting the same thing but it's separating it, right? And then, of course, when it comes to this categorical or qualitative data type, we also know that before we start creating any graphs for this, we do ask ourselves things like, well, first of all, is it categorical? And second of all, do the categories overlap? So the graphs that we created last time, we did say before creating those, hey, this is categorical data, and no, it is not possible to be in more than one category at the same time. There is no overlap. So for example, last time we created this pie chart with our qualitative data. And notice here we have raw counts and we also have the percentages. We talked last time about the fact that percentages can sometimes be misleading. So having that baseline, having those raw counts can give us a little bit more information. I really like to see both. When you are reading a graph, just remember, even if something seems substantially different percent-wise, it really depends on the total number in that sample or in that data set. Here was the cake and ice cream that we saw as far as food preferences and male versus female. We saw that we have more females in our class. So that's pretty self-explanatory, I think, remembering that the pie chart does account for everything that was an option under, for example, this one, gender, and it accounts for 100% of the entries. Let's go down here. We also saw bar plots. Now, you may want to remember that we actually told this one under options. When we were creating this, we actually said, please go ahead and order this by count descending. So whenever we're making bar plots, these are appropriate for any type of qualitative data. When we're or categorical, however you like to think about it, when we're looking at those counts. Now, if we are looking at qualitative data that is ordinal, that has some kind of an implied order, small, medium, large, we would actually keep that data in the same order that makes sense to us on that bar plot or bar graph. Here, though, when we're looking at music types, there was no implied hierarchy, no implied ordering, so that's when the Pareto comes in nicely, where we tend to use count descending on those frequencies. And this is because a lot of times we want to see the greatest and the lowest. We like to see that trend, even though we're not looking in the same way that we might on something numeric. We like to see what's influencing whatever it is we're concerned about the most, the least. You know, that kind of gives us some easy referencing. So again, we saw this for music type, ice cream and cake. We have this, and female male. Again, these are all categorical or qualitative data types that we were looking at. So for this video, I'd like us to explore our numeric or our quantitative data a little more. I know that we noticed last class that things like summary statistics, okay, that was pretty exclusive to something being numeric, right? We did not get any summary statistics at all for categorical, right? It would be kind of weird to try to take a mean, for example, of categories, right? So looking here, we started off with this, let me make that go away, with the summary statistics. And let's see, graph types that we have discussed before. We have said that whenever we have quantitative data, we can, of course, like we just saw, we can create a frequency table or a frequency distribution. We can create a histogram. We can create a dot plot, a stem and leaf plot, and also a box plot. So we have several new options that become available to us now that we are dealing with numerical data. Now, I do want you to remember, you know, it is possible to go back and use those more basic graph types with something numeric. You just simply have to make sure that you've translated your data into intervals or make sure that your data is at least discrete. The problem is that they're not as powerful or as useful as these graphs that we're about to look at. So when possible, we are going to tend towards these kind of better graphs because they give us more interpretable features. We can look at trends a lot better. Okay, so first, let's see. And again, the graphs I just called out, that histogram, the dot plot, the stem and leaf plot, the box plot, all of these are just for when you're looking at a single column, a single variable, right? Before in your notes, you should be able to reference and remember that we did say things like scatter plots come in very handy, or even time series plots, which is like a scatter plot just simply with time on the x-axis. We said those come in handy when you want to compare two different numeric variables. But again, for right now, let's just take a look at single variable analysis. So I'm going to graph histogram. I'm actually going to do just like last class. I'm going to hold down the control button. I'm on a PC today. If you are using a Mac, you hold down the command button and select as many as you'd like for different histograms. Frequency seems fine to me, and we don't have to control any type of bin stuff because, first of all, we saw that this stuff, the way we entered the data, we already kept it pretty separate. But StatCrunch and most technology does a decent job of defaulting to decent bin sizes. You can go back later and modify these if you need to. Typically, rule of thumb, if you're modifying or you're trying to figure out a starting point for a histogram, rule of thumb would be between 5 to 7 intervals, usually is a nice starting place. Histograms can be the most misleading, so we do need to be the most careful when looking at these. I love them. I think they're great. It's just changing those bins and changing the width of those bars as we're looking at them. It can give you some different visual effects. So stay careful and cognizant of that, please. Okay, I think this is good. Let's compute. Now, technically on a histogram, your bars should touch. I think here, probably because of the fact that we did enter only whole numbers, it's giving us something like this, where notice when I scroll over the first bar, it's saying anything between 0, notice this symbol here, if I can, let's say, well, I can't, notice the 0 has a bracket. That means it's including 0. Notice that 5/10 has a parenthesis. That means up to 5/10. So, for example, if someone had entered in that they had 45 hundredths or 0.45 siblings, that would be strange since this is definitely a discrete variable anyway. But if someone had entered something lower than 1/2, it would go into this bar right here. So the count, we had one person in our class that had no siblings. They're an only child, it looks like. And then right here, how many do we have here? We have 15 students who have one sibling, 2 students with 8 siblings, and 5 students with 3. And 4 students, or excuse me, 1 student with 4. Did I say? I hope I said here 5 students with 3. Anyway, the frequency is telling us the count of how many times someone fell into that range or that little interval that we're looking at on the histogram. Again, technically a histogram is typically continuous. It typically will have those bars touching when possible. Let's see if another one does a better job. Notice here on pets, that's looking a little better. So here on pets, we can see that these bars are connected. Which is like what we usually prefer to see, because we will be transitioning into trying to look at not just the shape of these, but we're going to try to imagine a smooth curve and eventually start talking about the bell-shaped distribution and other types of distributions. So even right now, while we're looking at these graphs, I do want you to start noticing some features. Features that you should pay attention to. The shape of your graph. Right, the shape of this histogram, because now suddenly this number line on the x-axis, this has some order to it. So we can start imagining for ourselves, sketching a smooth curve, for example, over this, and talking about features such as how many curves do I have? Features such as, do I have any outliers? Is there something unusual here, right? And then, of course, features like measure of center, the mode, the median, the mean, which we will also explore a little bit more later on. But let's go back actually to the first one, siblings. What you'll notice here is this right here would be considered unimodal. So when talking about the number of bumps that we have on a picture, or if you're doing the smooth line in your mind, you would say, okay, hey, look, that's one big curve right there. I can see the bump, right? This right here would be called unimodal. If you have more than one bump, you would say this is bimodal. And then beyond that, you would start to say, okay, well, I have multimodal data if I see more than just 2 modes or 2 bumps on the graph. This is unimodal. It's not very symmetric. Symmetry is something that we also like to look at. Symmetry being, hey, if I look at this graph, can I see a place where if I wanted to reflect and cut the graph in half, both sides would literally match exactly onto each other, or pretty darn close, right, onto each other, so that I could say these frequencies are matching up. This is not the case here. Notice we have a much lower frequency here for no siblings than we do here at 2 siblings. On this one, we would say this is still unimodal. I think I mentioned that. It's actually getting very close to another graph type that we have, maybe not that close. If you ignore the first bar, okay, and you look here just in the center, do you see how these bars are getting kind of close to each other's heights, particularly between 2 and 5? If we were only looking, for example, at a graph like that, we might say, you know what, I do see that there's more frequency here, but with these frequencies being so close, we're actually getting kind of close to something called a uniform distribution. This one, again, is not really fitting the bill as far as being uniform. I do want to let you know, though, that when the bars are equal height or very close to equal height, you would say, hey, this is approximately uniform. It's approximately equal between all of the different intervals or all of the different bars. Oh, this one's beautiful, huh? Look at that height. It's interesting, though, that typically on a bell-shaped distribution that we'll learn about more later, the mode will actually be the tallest right in the center. So here, technically, this would actually be bimodal, I guess, because of the two tall bars that are equal to each other. But a lot of times this right here would be the highest. And this one actually is almost bell-shaped. In real life, it would be bell-shaped for the population, by the way. I know we used a convenience sample, but a lot of times you would get that nice bell-shaped feature off of height. Okay, so there we have histogram. While we are looking at histogram, let's do something. Let's create a second histogram really quickly. And we'll do the same thing. We'll do it for siblings, pets, and height. This time, let's create relative frequency, because I do want you to already begin to see a connection between looking at the percentage of data values that we have in each bar, that distribution, that balance from one bar to the next, or one interval to the next, when we are looking at over here percentage versus frequency. Notice, of course, that on the relative frequency histogram, we do have decimals here on the left-hand side, right? Because getting a whole number of 1 would mean 100%. So seeing right here 5/10 or 0.5, here we're saying, hey, look, that's actually like half of the people in our class has one sibling. So it starts to put it actually into a really cool perspective, rather than being here and saying on the regular frequency histogram and saying, hey, 15 is my frequency. Both things do provide value. Percents can actually be quite nice when still being able to see the original context, especially. I do want you to notice something else, though. You may have seen it on the first graph, but look here at this one. In addition to having the added power of relative frequency showing us percent very quickly, right here, one pet, we have 30% of the people in our class, right? Which the count for that is 9 people. And in addition to just seeing the percentage, please notice the balance of these bars. I mean, like the height, right? Like right here, the height of this first bar compared to the second bar. Over here, the height of the first bar compared to the second bar. What I want you to notice is that the pictures actually look identical. The only difference here is the y-axis, whether we're talking in terms of a literal count or in terms of a percentage. This is very important for you to notice right now, because very soon when we begin talking about percentage under the curve, I want you to remember that even though a lot of times, if you're similar to me, a lot of times we go towards putting regular frequencies up originally when looking at the shape of the distribution, we could have just as easily have talked about percentages. And those percentages would have meant something to us, right? So, for example, I could have said, hello, class, what percent of students do we have that have between 2 to 3 pets? Or, let's see, we could say maybe that's 0, 1, so equal to 2 and equal to 3, yeah. Maybe between, let's see, so let me do something. Let me clear all these little pink things I've created. And let me click here. What I'm saying is, what percent of your classmates or of our group have pets between 2 and 4, right? Where we're not including 4, we're saying less than 4. What we can do here is we can actually add up these percentages, right? We can say, hey, look, that's about 16%, right here's about 23%, add that up, and now we have a percentage, looking at our sample, a percentage of people that have 2 to 3 pets. Which, if we had a good sample, again, we had a convenience sample, ours was not good. If we had a good sample, that would actually empower us to later on be able to start thinking about those percentages in terms of probability, right? And be able to think about these in terms of like being empirical probabilities, where we're saying, hey, look, from my data, I observed this percent likelihood. So now I'm going to start making some assertions about what I think may be going on out there in the real world. You could have gotten the same thing again over here from the raw frequency. You would just have to say 5 added to 7, now divide by the total number of people that we had in the sample, and you would still get that same percentage. But again, I want you to notice the balance, and I want you to already be seeing that histograms are giving us an element of power that we did not have with regular bar plots or bar graphs. That power being, we can read left to right like a book, and as we're doing that, we can begin discussing little chunks of this number line, little zones that we're interested in for our variable. We can begin discussing the probability, or at least the percent of occurrence that we have observed. Inference is a little bit, it's a step beyond this, but this is a very good starting place for you to begin seeing those percentages already coming out of the data for you. Okay, so that was histogram. Let's take a look at stem and leaf. And we'll do the same thing for every single one. I didn't look at height again, did I? Height would be the same way. It's going to have the same shape, just like what we just discussed. Now, this is a stem and leaf plot. Different pieces of technology will describe or give you a key in sometimes a different way. The way StatCrunch describes your data, or the graph here, is it lets you know the leaf unit. So right here, do you see the double zeros, double ones, double twos, threes, four? Right here on the left of the colons, this is called the stem, okay? Over here on the right-hand side of the colon, these are called leaves. And sometimes they actually have something besides 0. We'll look at a different stem and leaf in just a moment. But the way these things play is, first, this 0.1 is telling me that the 10th place here, that this leaf right here, this is 0, let me highlight it, that is actually in the 10th place. So when I interpret this, I have 0.0. When I interpret this down here, that is 1.0, right? And every single one's actually 1.0, 1.0, 1.0, over and over and over. So in a way, actually, if you wanted to kind of turn your head to the side, you can almost see something similar to a histogram, right? You can see the frequencies going on here, where the intervals are by whole numbers, right? And we can see, for example, that we have 1 as the frequency of students who had no siblings. And then I guess you could count or just observe the height of this frequency for 1 sibling, how many students had 1 sibling. And you can kind of even see that balance. Remember I said already start imagining a smooth line going over your distribution, right? Start looking at that shape. You can already see well, other than this part right here, we can see something that is unimodal. Definitely a lot of students have exactly 1 sibling. And then we can also see kind of this decreasing on the right-hand side. I would say, yeah, I'll talk to you more about having tails on your shape in just a moment. This one may not be the best one to do that with, but we'll start talking about outliers and things of that nature too. This one's looking a bit more balanced. Right? Again, when we were looking at pets, let's see. I don't know. I guess I would still say this one is unimodal. Let's go back to the histogram really quickly. Yeah, okay, that was pets right there. I'm still inclined to see that single mode right there. So the reason we have these different graphs that we pull up, though, is because sometimes from a certain graph we may have a different perspective or see a different pattern. So as of right now, I'm saying I'm tending to think this is relatively unimodal. There's one highest bar, and things seem to be clustering somewhat normally here, right? Not normally as in the bell shape. Normally as in, I have a high bar and then it kind of gets lower. I should be careful with my vocabulary there. But beside that mode of 1 pet. We may even have an outlier over here. 2 of us had 6 pets. I was one of them. Okay. Yep. So we'll talk about defining outliers a little bit later. But for right now, just know that on the picture, usually they're going to be a little bit further out from where the rest of the data is. That's one way to identify visually. In fact, if you were drawing a smooth curve over your data, sometimes you may even be able to see kind of an extended tail. I'll give you some visuals in just a little while. And then we would say, hey, that looks like it's right skewed. I see this outlier. If I were tracing over this data here, this outlier that's pulling my little picture a little bit more to the right. And the skewness does affect the most appropriate measure of center. Mean I'll go ahead and tell you, is the weaker of the two. While it does take every single data value into account, if there's outliers, the mean will jump and kind of get drawn closer to that extreme value, while the median is the literal center. So whenever we have something like unimodal data, that one bump on our data, the median does a great job of counting right smack to the middle and giving us a pretty good measure of center. That's height. Ooh, height looks weird there, huh? They really clustered that together. You know, and something I want you to notice here, actually I think all of them did a double stem and leaf. Let's go back. Yep, actually every single one defaulted to double stem and leaf. So what a double stem and leaf is that's when instead of just saying 0 and counting all of the zeros together, right? Like here we're just 7s all together. That's actually by accident because there was no one over 70 equal to or over 75 inches. But a single stem and leaf plot would just simply have like 6, 7, 8, 9, you know, just one of each number along that stem. A double stem and leaf plot is splitting these numbers in two to kind of give you, you know, more maybe reasonable bin sizes or intervals. So, for example, here, this upper 6, this will hold all of the heights that were up to 64 inches. Once you hit 65, it's almost like rounding rules. You jump down to the second stem for that 6, right? So a 5, 6, 7, anything like that would be down here. Notice again the key is modifying depending on the data. Here we have leaf unit equal to 1. So as I read this, I'm going to see a 61, right, for the first piece. And here's another 61, 63, 64, 64. So this is the way we read it, right? Down here we have 66, 66, 67. So again, the leaf unit lets you know, the key describing the leaf unit lets you know where this number right here on these leaf values are falling so that you can then interpret appropriately. So these right here, if this is the ones place, then this over here is the tens place for those stems, right? That's why we're saying 61, 66, 70. Over here with pets, again, we're using the tenth place, so these are whole numbers right here on the stem, and every one of these is just a decimal. Okay. Let's see. Let's go ahead and take a look at the dot plot for each of these. I really wanted them on separate graphs. Oh well. Okay. In fact, let me see if I can just edit that and change it. Actually, I'm just going to take off a few because I really do not want them all in the same picture. So let's just look at height, for instance, first. So here's height. The way a dot plot works is you still have this x-axis, right? Which is nice. Numerical data, it's great that we have this x-axis where numbers are actually working the way we would imagine. The lower number on the left, the higher number on the right, and you can actually read left to right. And so as we're looking at this, what happens over this number line is we get a dot every time one of our data points is falling over that value. So right here for 64, every time someone is 64 inches tall, we have these stacking up dots. So again, it's showing me frequency almost like the histogram, except notice with height right here, let me just change these to height also so we're looking at similar things. Okay, notice that with this dot plot, things look a bit more spread out, right? Whenever we have intervals and decimals and things like that, a dot plot usually is much better about showing me the original numbers. So is a stem and leaf. And a dot plot kind of is the middle ground between a histogram and a stem and leaf. Remember that stem and leaf? Do I still have that thing somewhere? Come back, stem and leaf, come back. Let's see. We're looking at high. Okay, good. So between these three, usually the histogram is the one that will be the most ambiguous for what exact numbers are. So for example, a lot of times whenever data has been recorded to say the decimal places, right, instead of me knowing exactly that someone has reported being 64 inches tall, I might say, hey, well, this person has said they're between 64 to 66. It could have been anywhere in between there because we had decimals in our data, right? So with a histogram, you generally lose the original data points. You start to see the patterns, but you've lost some of that kind of up close view, right? Over here on the stem and leaf, you do not lose any of your numbers. You get all of them. And so you still see a trend, you still see a shape, hopefully, if you're turning your head sideways in your mind, right, on that stem and leaf. And it's different, which is, notice it's interesting. They've clustered the things up differently. That's again why we want to see different views here. But we're seeing every single individual data point. And then a dot plot, it's even more individualized. I think I said it backwards a moment ago. It's even more individualized than either of the other two. Stem and leaf would be the one that's in between, right? It's the one that still has some intervals happening. Like here's anything below 65, 61 to or 60 to 65 inches right here in this first little section of leaves. Versus over here on the dot plot, legit, they have, unless there's some minor rounding, they have put exact numbers, no grouping of the heights at all. So when we're seeing these frequencies, we're seeing counts literally for each individual item. So the most detailed is the dot plot. The next most detailed is the stem and leaf. It steps back and kind of magnifies less, I guess we should say. Like you're looking at a less close perspective, and you're saying, hey, now I'm going to see the original values, but I'm going to look at groups. And then the histogram is like, it's almost like the furthest back step as far as looking at this type of picture where you can actually see the shape very nicely and those, the frequencies showing pretty clearly here. With this thing, we're stepping back usually and we don't know exactly what's in each bar. We can just see that balance and the count within each interval or each class. Now the last graph type, I'm not going to describe it too much here. I will show you how to find it. It's called a box plot. And again, this is the last graphing type when you're just looking at a single variable by itself and trying to understand its the patterns within its data. So a box plot, I'll create one. Let's do height since we're looking at height right now. I like this thing to be horizontal. It makes me happy, so I always click that. A box plot plays a bit differently than these other graphs. That's why I'm going to create a new video in just a moment. It is one of the main graphs though that we look at. In fact, some statisticians really like to pair up either the dot plot with a box plot or maybe stem and leaf with a box plot. My preference, I love histograms and I love box plots. I like to see those together. So stay tuned for the next video where we're going to look at how this right here is also describing the balance of my data. I can't see raw frequencies as easily, but I can still see the balance of my data.